welcome to the Specialist Maths 3-4 lecture. Let's get started. Welcome to the HR Notes lecture series. My name's Michelle. I graduated in 2018 and my VCE subjects were mainly maths and science subjects. So I did specialist, methods, physics, chemistry, bio, and then just mainstream English. And I thought that those subjects really helped each other when I was going through in VCE, and definitely all of the skills and kind of problem solving skills do still help me even in my course right now. So I'm currently in the final year of med, so nearly all the way through, I guess, and definitely all of those skills are very transferable across, even though we might not be doing as much maths as I was doing in VCE. So just a quick thing about HR Notes, we've been around since 2007 and our mission is to help students like you thrive as much as possible and kind of support you through the VCE journey and now into university as well. And we want to provide as much resources and as much accessibility as possible, and we've been doing these lectures since around 2015, so we've kind of moved to some of them online now so that there's greater accessibility, and hopefully you find these helpful. So just a sample of all the resources that we have available. We have stuff from study notes to articles to things. So we have some written things like articles, newsletters, and study notes. And those are all really helpful, especially kind of if you like a subject like this for methods or for physics where you're allowed bound notes into the exam. It's really helpful to see what other people have written as their notes, and it's helpful to see kind of what has been done so far, because by knowing what other people have included in their notes or what other concepts, we can kind of get a larger idea of what things we need to include or what things we should emphasize in our study. We also have things like videos and lectures, and like the lecture you're looking at right now, to kind of get that multimodal way of learning. So do definitely check that out. And if there's any questions or any concerns, you can always reach out to us on our forums as well, and on our discussion kind of pages. We also have a lot of other resources as well, like Cheat Smart, Study Guides, and Edu Unlimited. So definitely have a look into those if you want just that little bit of extra help or you want to have a bit more resources to use. I also want to extend a special thanks to La Trobe University and our other university sponsors. They're really trying to support your learning and doing it for your benefit. So make sure to check out the early entry program into La Trobe University and have a look into that if you're interested. Okay, so let's just chat about what we're going to be going through today. So today's plan is we'll start on circular functions and go through differentiation, integration, applications of integration. So this is going to be a very calculus heavy topic. So the other bit of calculus is differential equations, which we won't be going through today, but the other two components, so you have differentiation, integration, and applications of integration as the kind of core calculus topics, and then we'll have like kind of the applications of calculus, which is the differential equations and the vector calculus, which we won't be chatting about today but might be chatting about in the future, but do have a look out for that. So that's kind of the other half of the calculus topic, and we'll also be talking a bit about circular functions, which is a topic that is taught throughout methods and spec, but a lot of people find difficult, and fairly so, because they can be quite tricky at times. The main thing I want for all of you to do this lecture is to ask as many questions as possible, ask about any concerns, ask about any questions, bring anything up that you would like to, because I think it's really important that you tell me what you are concerned about and what questions you might have, because that way we'll be able to all learn together, and if you have the question, it's very likely that other people have the same question as well, and if we can all learn together and learn the reasoning behind different things or kind of figure out why certain things go on, we can kind of learn the content a lot more deeply. So these topics can be a little bit tricky, so make sure to ask about questions or concerns or anything that you're really curious about. And if there's anything in particular that you're concerned about, just in general, do make sure to ask questions about that as well. Alright, let's jump into trig and circular functions. So there is a couple memes kind of sprinkled out here and there, so hope you enjoy them. Okay, so the kind of the new topic that's a bit different to methods is these inverse and reciprocal circular functions. So you will have seen some reciprocal functions in methods, but you most likely haven't seen inverse circular functions before this time. So there are these two new families, and they're really good to have in the reference book to just kind of keep it and like to have the different ones and how they look and how they can be translated in the reference book. I would say for reciprocal functions, they're probably, the graphing of them is quite similar just to graphing the normal function, and then essentially just flip it. For graphing the inverse circular functions, we'll talk about a system to kind of graph them and work through them, but I find them easier to graph than just the ordinary circular functions because they're a lot more structured and there's kind of less things that can go on with them. So try to memorize the shape of the graph, or I would say more than memorize, just kind of be familiar with the shape of the graph and know approximately what it looks like. A lot of them you can kind of, because they are kind of manipulating the circular functions we have in the first place, there's a lot of things that we can do just to kind of change. We can kind of, from first principles, logic what they look like, but obviously it is easier if you know the general shape of the functions and know what they generally look like, because that way you know what to expect when you're kind of doing these types of things, and also it might just be a more efficient process for you overall. But I would say that just try and be familiar so you know approximately what types of graph it looks like. If you really can't memorize it, you can always kind of build it up from first principles. So a reciprocal function, just applying reciprocal function things to circular functions, and applying like inverse function things to the inverse circular functions. So a couple things that you need to know is the domains, the ranges, and the transformations, how to sketch them, and how to solve equations and inequalities involving them. Righty. And you will have to do calculus with them as well. I would say that calculus you'll get like, in your bound notes, you'll get a whole set of kind of equations to do the calculus for the inverse circular functions. You won't really have formulas for the reciprocal functions besides sec because of its relationship with tan, but you should be able to first principle logic it using the chain rule along with the differentiation rules you already know. Alright, cool. Let's talk about reciprocal first. So what we do is we just put the trig in the denominator. So cosec is, let me get a pen up. So cosec is going to just be 1 over sine. So cosec is going to just be 1 over sine, which is what we have here. And we'll have like cos equaling to sec and tan equaling to cot. So the most important thing here is that we recognize what each of these things are. So the easiest way to memorize this is cot is kind of unique by itself because just like tan and cot, they're like the odd black sheep of the family. They're that odd one that's kind of left out. So it's like if you had twins and then like, I don't know, another brother or sister, it's similar, but it's always not going to be the exact same, right? So for sine and cos, because there is a really intimate relationship between the two, I kind of focus on trying to not confuse those two together. So the letters swap, so sine goes to cosec and cos goes to sec, and then tan goes to cot. Okay. I guess you can kind of remember the tan goes to cot as both of them include t's, right? And it's the only ones that include t's in all of them. Alright, so how to draw these without memorizing? We have to draw the base trig function, and then we draw the vertical asymptotes at the x-intercepts, and then we can so we draw the base trig, so let's just kind of go through that together. So let's say if we're just drawing the base sine function, and then we draw asymptotes at the intercepts because 1 over 0 is undefined. So we'll have an asymptote there, and asymptote here. And then remember, for reciprocal functions, max becomes mins and mins become max. So we'll have a minimum here and a maximum here. And importantly, if there's no vertical translation on the thing, there's also going to be an asymptote kind of y equals to 0 as well, because we'll never be able to get a 0 point in terms of we'll never be able to reach those 0 points that we reach by the x-intercepts. Therefore, we'll also never be able to reach 0 on the axis here as well. So that's what you kind of see there. And then that's kind of the graph we get, and you just repeat it for how many periods you want. Evidently, it's a bit more funky once we get talking about, actual transformations and stuff. But the easiest thing to do is essentially just do this. Reverse the function that they've given you, and just do this until you reach to a point. And then, because it might give you something like cosec 2x plus 3 plus 5, right? So, or like 2 cosec blah blah. So what I would do is I would focus on I would get away from I would get rid of the plus 5 for now, and I'd focus on this segment and find what a half, that says should equal to cosec rather than cosec. I said cosec, but I wrote cos. So cosec, so that's going to just be a half sine 2x plus 3, right? And then what we're going to do is we find out how to graph that one first. And then once we do that, all we have to do is just put the plus 5 at the end for what that is, and we can find the new x-intercepts, draw in the new asymptote, etc. But the actual coordinates of all the vertical asymptotes will be the same, and the turning point, x position should be the same, but everything's just going to be shifted 5 upwards. And I find that's the easiest thing to do, especially when you have a lot of transformations going on. For tan, so the tan function is like this. So the cot function is literally just the reverse of that. So it has the asymptote here instead of here, and these become x-intercepts. So essentially, when we have this, we'll have this instead, and it'll just go down like that. So it'll come that's an asymptote. So it'll come like that, and then we'll just have, we'll have this bottom half of the function there. Sure, a little bit too forwards. Oopsies. Okay, so we'll have this bottom half of the function here, kind of coming into here, and then we'll have the top part coming up there. So everything that was an asymptote before now becomes an x-intercept. Everything that was an x-intercept becomes an asymptote. And a cot graph is pretty easy to draw just by itself, because it's essentially just a reflected tan graph. Or you could even say it's like a reflected and then translated tan graph, essentially. Okie dokie. Alright, so let's chat about each of these functions a little bit more in detail. So cosec nx is 1 over sine nx, like we talked about before the letters swap. So importantly, the domain is no longer just R, right? Because now we have asymptotes there. And if we think of where the asymptotes would be located, they're going to be located when sine nx equals to 0, right? And we know that sine nx, so sine in terms of when it equals to 0 is here and here, right? So 0, pi, 2 pi, 3 pi. So therefore we're going to think that it's going to be basically pi n, or pi k, let's say. So it can be any number of cycle of the pi kind of numbers. So therefore we're just going to get x equals to pi k over n. And that's where we can kind of see what's going on. Alright. So then in terms of the period, it's going to have the same period. So that's the like domain. That's why we have that asymptotes there. In terms of the range, it's just basically because of that's where the minimums and maximums are, and like the smallest value versus the largest value, and that's why we have a range which is excluded there. But if there was manipulation, so if this was like 2 cosec nx instead, there would be differences in where it would be. Like this would be a half versus this being -1. So it kind of just depends on what the vertical, like what is the values here and here. As in, is there any vertical translations? Is there any dilations from the x-axis? So that will kind of determine which range of values cannot be taken. Essentially, all you need to look for here is where is the difference between the two turning points, and then you can just put that into there. The period is going to be kept the same because it's the same function except just 1 over the function, so the period is going to be unchanged. It doesn't change how much time it repeats over, and we already talked about the asymptotes. Cool. So sec is very, very, very similar. It's just 1 over cos nx. And remember, that's just basically because of the relationship that sine pi on 2 minus x will just equal to cos pi on 2. Cos x, right? So that's why it's just literally a shift in terms of where it's really going. So what we're going to do here is we can kind of see that now the asymptotes, now we're looking for when cos nx is going to be equivalent to 0, right? And we know cos, in terms of where it's negative, it's going to be, in terms of when it's 0, it's going to be here and here, right? Top and bottom. So it's going to be pi on 2, 3 pi on 2, 5 pi on 2. So it's going to be every negative pi on 2. And we, doing kind of the proofing topic and all that kind of stuff, we might be a little bit more comfortable with how we can phrase that now, because it's going to be every 2k, which is the even one, plus 1. And that's going to give us our odd one over 2n times pi. So that's going to give where our odd asymptotes are. And the n component is just because we have the n there. Cool. Once again, the range is just going to be everything excluding the space between the minimum and maximum kind of turning points, and that's going to tell us where it is. Alright, so then the period, once again, it's going to be unchanged because the putting 1 over something isn't going to change how often this graph repeats. And then we already talked about how the asymptotes work there. Okie. So with cot function, the cot function is essentially the exact same as the tan function, except it's been translated across backwards by pi on 2. So this point will used to be here, and it's been reflected in the x-axis. So that's really the only two differences, but it just still looks like a tan function. So importantly, now we want to know when tan nx would have equaled to 0, and we know that's going to be at this position. So once again, it's going to be k pi, so we're going to have k pi equals to nx, and then x would equal to k pi over n, which gives us our asymptotes. The range, just like the range for tan is -infinity to infinity, the range for cot is also -infinity to infinity, because as it approaches the asymptotes, it's going to go to positive infinity and negative infinity. The period is unchanged once again. Sorry, that should be pi over n rather than pi n. So it's going to be unchanged compared to what it was before, because putting 1 over something isn't going to change how often the graph repeats. So we already talked about the asymptote, and you can kind of see how if we said pi on 2 minus x, that's going to be, so that's a translation of pi on 2 to the right, and then we reflected it in the x-axis. Reflected it in like the axis, right? Because we've just kind of made it positive to negative. Cool. Awesome. Alright, so these are the formulas that we need to talk about. So these formulas, most of the formulas should be in your formula sheet, but I think all of the formulas here should be on your formula sheet. They are really, really, really good. Like, they will come up so much through complex numbers, through calculus, through circular functions in itself. They come up so much, and they can be very useful in any type of like topic essentially, because they can come up like, cause circular functions can be integrated into any other of the topics that we're talking about. So it's really good and useful to kind of know what they are and how to use the formulas appropriately. So even though that they are on the formula sheet, it's good to have them at the back of the mind, especially for efficiency. And sometimes you'll have to do something called the half angle formula proof. So what you do instead is, so when we look at something like this, so we have, instead of doing like the half formula, so what you do instead, a really common example is like cos pi on 8, and essentially you just make cos 2 times pi on 8 equivalent to cos pi on 4, and then you kind of work backwards from there. Right. Inverse circular functions. These are good to kind of memorize the shape of the graph and like just kind of know the gist of the graph. You can always use first principles, but it's always useful to kind of know what they look like. And because they're inverses, they're going to be cut off at certain points because of the turning points involved in a circular function, so that we can have a one-to-one curve. So how we can kind of draw is, if you didn't want to memorize it, you could just draw the basic trig, try to reflect it across the line, and then take the maximal domain to be one-to-one, and then kind of restrict and do whatever you need to do from there. Another thing is that if the inverse is on the inside, we can kind of cancel it across. If the inverse is on the outside, then we can't cancel it across. It's not always equivalent. And that's essentially just because if you think of something like, let's just use sine. So sine inverse of sine, actually let's talk about on the next slide because it would make more sense once we can see the domains and ranges of these functions. Alright, so for this one, right, the domain is negative 1-1. That's just basically because the base sine function, remember, it can only go from, the amplitude is at max negative 1-1, and that's because of the properties of the unit circle. That's the maximum values that sine and cos can really take, because of the unit circle only goes 1 to negative 1, right? So that's why it's the domain, and because it's the inverse, this was the range before, but now it's flipped into the domain. Okay, so in terms of the range, this is literally just arbitrary. Like, they've just picked a point which is a little bit arbitrary, and to be very honest, like, it doesn't really have any real particular reasoning why they chose this range over like a period before that or a period after that. Like, there's not really an implication per se of what they're trying to do here, unfortunately. So they've just tried to exclude any turning points, but there's no reason that it couldn't have been pi on 2 to 3 pi on 2. Like, there's not really a reasoning for that. It's just what they chose. But what we just need to remember is it's negative pi on 2 to pi on 2. Okay. So let's go back to that thing of sine inverse sine x does not always equal to x. So if we imagine sine inverse sine of, let's say, 2 pi and 3, right? Okay, so this cannot be equivalent to 2 pi and 3 because that's outside of the domain, outside of the range for sine, right? Like, that's not possible. It's outside of the range for sine inverse. So what we have to do instead is, when we look at this, what happens is we have sine inverse, and then we'll have something like, so 2 pi on 3, that's in the positive quadrant of sine, and pi on 3 of sine is just going to be root 3 on 2. So then we can kind of convert it backwards to what equivalent would be in this domain, in this range, and that would mean that the equivalent here is going to just be pi on 3, right? Because in pi on 3, when we sub it into there, it's going to be equivalent. So yeah, so we just need to keep that in mind in what we're trying to do. Okay, alright, so for cos, the domain is the same thing, because once again, you can only go from negative 1 to 1, and that's kind of the maximum values you can really take for the base cos function. But then in terms of its range, once again, it's a little bit arbitrary, so they just took 0 to pi, so 0 to pi, and it's very arbitrary in what they actually took in terms of the values. So my honest opinion is they just took negative 1 to 1 and picked one of the sets of values that it could be. So there is no reason why they didn't pick, let's say, for example, they could have also done pi to, they could have also done, yeah, they could have done pi to, let's say, 2 pi as well, or they could have done negative pi to 0 as well. Like, doesn't actually matter too much, because regardless of what you're doing, negative pi, they're always going to give you the same values of what you're trying to do here. So this could have, if we drew like another version of this graph along, this could have been from, if this was pi to 2 pi instead. So our domain here would have been negative 1, right? So that would have been negative 1 pi, negative 1 pi, right? Because when we sub in negative 1, we're going to get pi. And then if our range was there, it would have just been a translation. Sorry. Would have been a translation up to the 2 pi, right? Because when we sub in 1 into there, it would have just given us pi instead. Would have given us 2 pi instead. So there's not a particular reason, unfortunately. It is just what convention they, like what values they chose to really stop it off at. Because if you imagine the graph of, our graph of 0 to pi, it's going to look something like this. So 0 to pi, like that, right? There's no reason that they couldn't have taken it this side, or they couldn't have taken this side, except that I guess if you look back at the two graphs, you would like be elevating it above the axis or putting it below the axis. So you could be technically, like, you would be able to get something like this instead, right? That would be your graph instead. But in the large scheme of things, it doesn't actually matter too much. They just picked a thing and went with it. Okay, cool. So the tan function is arctan, and it just looks like a cube root function, to be very honest, but it's just a tan function on its side. So because the asymptotes were this way before, now the asymptotes are horizontal. So because the asymptotes are horizontal, that means we just cut off the edges of the range that we're working with. And once again, because if we went across that way, if we think about a tan function normally and it goes like this, like that, if we cut across there, we can see that more than one value is possible. So they just chose one of them to use, and that was the negative pi on 2 to pi on 2, 1. So that's really just it, what they did. And the domain here is R, so remember the domains and ranges flip. So the domain before was R, the range before would have been R, and now the domain is R, and before the domain would have been like excluding every odd pi on 2 type thing, but now because we're only using one thing, we can just write it as negative pi on 2 to pi on 2. Cool, awesome. Alright, let's chat a bit about how we evaluate these. So the first one, what we're actually trying to ask is what angle will give you a half when we put it into sine. And if we use our wonderful triangle here, we're going to be using the 2, 1, root 3 triangle, and we're looking for a half. So sine is opposite over hypotenuse, so therefore we're going to be looking for pi on 6. So this is going to just be equivalent to pi on 6. Cool. Alright, so cos inverse of cos negative pi on 3, right? So what we have here is that situation from before. So if we think of where cos pi on 3 is, negative pi on 3, it's here, right? So cos negative pi on 3 is going to give you just going to give you positive a half in terms of the value of it. And what that means in our terms is now we have to think what value of cos inverse will give us a half. And remember, our domain for cos was 0 to pi. So therefore, if we want a positive one, we would just be thinking that's just going to be normal pi on 3. So the thing we have to be really careful about is that it fits within our domain, because we can kind of do a quick check. If it was to fit within our domain of, if this was just pi on 3 or 2 pi on 3, it fits within our our range of our function. So therefore we can just accept it straight away, but because it doesn't, we can't really accept it. Cool. Okay, so this one has the normal function and the inverse on in the inside, but the only problem is it's not the same function. So not the same function. So therefore we can't do the thing from before where we just directly rule it out. Instead we have to kind of go into a little bit more detail. So the thing with this is we think to ourselves, okay, negative pi on 4 sine inverse. Yeah, that's just root 2 on 2. Nope. It's actually, because it's the inverse of it, it's not asking for the sine of negative pi on 4. It's asking for the sine inverse of negative pi on 4. And remember, sine equal to opposite over hypotenuse. So what we can actually pop down is that this is going to be the equivalent of saying that this part is going to be 4 and this part, let's just say it's that angle there, this part is pi. So therefore, using Pythag, you'll get that this is 16 minus pi squared in terms of the last side there. Alright, so then we have to decide whether this is positive or negative, right? Because if it's positive or negative, we'll kind of determine which side it is. So if we consider sine of inverse pi, like negative pi on 4, sine is only negative when it's in this or this quadrant, right? That's a thing for us. It's only ever negative when it's in the third or the fourth quadrant. And that would mean that this angle, the result of this would have to either be in the third or fourth quadrant. Now, then we have to say to ourselves, okay, is it going to be in the third or fourth quadrant? And in fact, your calculator will do the same thing. If you pop it into your calculator and try to put in the answer of like what this is actually equivalent to, it will try and do the same thing as you've been doing kind of up here as well. So we have to decide whether it's the positive or the negative version of 16 pi on 2 minus, not pi on 2, pi squared over 4, right? Okay, so we kind of need to know a little bit more details about this as well. So we know that the sine inverse, the output of sine inverse, right, can be from -1 to 1. So what that means for us is, in terms of the values, it can be in here or in here. So it can be -1 or 1. So it can be either here or here, right? Because we're trying to sub it in for the angle. So it can be in like this part or this part. So we kind of get that it's going to be here or here, right? Which doesn't really help us conclude where we're really going. But essentially, when we look at this and we can see that this angle is going to be a negative pi on 4 rather than a positive pi on 4, we get that this value is going to be a negative. And then when we sub in the negative value into whatever this is, right? And because also, you know that sine of, so pi on 4 is approximately about 3.14 ... right? So therefore we know that it's not going to really reach it's not going to reach this, like when we have that over 4, right? It's going to be 3.14 over 4 ... right? So we're going to get that this is going to be 0.9 something overall. So what that means is, because pi on 2 is about 1.7, we know that it has to be in this quadrant instead, because it's about 1.7 something. So if it was in this quadrant, it should be bigger than 1.7 in terms of when it's a negative value. So therefore we can kind of conclude from that we just have root 16 minus pi squared over 4, as we have that this number is actually smaller than pi on 2. Right, because that's really the only conclusion we need to find. Is that this number bigger than pi on 2 or smaller than pi on 2? Cool, awesome. Alright. So then what we can look into is the domains and range. So this is a really nice table to kind of work with, and I think it's a really good one to kind of utilize and have handy. So with domains for our inverse circular functions, what we want to do is undo the transformations, because we must have everything fit between the -1 to 1, right? So we make whatever's on the inside equivalent to that, and then we kind of undo all the things. With ranges, we have a base thing of it's between -π/2 to π/2, or it's between 0 to pi, and then from there we kind of can expand out, because things and stuff are being added to them / timesing them to make it bigger and bigger. So let's have a look for this question. So let's say we have a sine inverse b x minus c plus d. Okay, so for the domain, we undo. So we take the bracket out. So we take this part of the bracket, and then we apply the -1 to 1. So we get just bx minus c, and then we need to figure out what x values it can take for that to be able to be happen. So we put the c across and then divide by b, which gives us, it'll be c minus 1 over b to c plus 1 over b. Alright, so then for the ranges, what we do is build up. So we have the base range, right? And we say that y minus d over a is equivalent to the base range. And then we can kind of build it up by there. So we times everything by a and then add the d across to kind of get the overall range of the function. And this works the same way for cos as well, and for tan, so this works the same way for cos inverse as well. For tan inverse, I guess the only thing is that the range would work in the same way, that we kind of can build it up, but the domain you don't need to really investigate that much because it's already R, so regardless of what we really do to it, it won't really change it too much. Cool. Alright. So solving equations, it's essentially just everything the same, except we just need to make sure that we have, like, we're just integrating reciprocal and inverse functions now. So the thing is that you need to make sure you have it in the correct domains and ranges, specifically, especially for when we're talking about like the inverse functions, because they have a very specific range and domain. So make sure you use a lot of compound angles, make sure you use a lot of double angles, and then for these types of questions, we kind of did that type of questions, but just use like triangles to help you visualize what's going on. Cool. Alright, so let's go through solving this question together. So it's sec 2x equals to cosec 4x. So the first thing that we can kind of identify from here is sec, remember that's going to just be 1 over cos 2x, and this is going to just be 1 over sine 4x, right? Okay, because they're both 1 over, we can just flip both of the fractions and to give us the same thing. So now we'll have this as cos 2x minus sine 4x, right? Okay, cool. So then from there, we can kind of solve from there. And a really important thing for just circular functions and maths in general is that you don't just like reject a solution and kind of expel it into Narnia. You must actually keep all of your solutions and just minus things across until, so it's kind of just like if you had x minus 2 equals to 0, you wouldn't suddenly just be like, okay, x equals to 2 equals to 0. You would still keep the stuff from before as well. You would say x equals 0 or x minus 2 equals to 0. Okay, so we need the same base in order to solve for these. So we're going to change this one using the double angle formula to change this one into this equation instead. So 2 sine 2x cos 2x instead of sine 4x. And then what we're going to do is group, just like if we had x squared minus 2x, and we could group it into x minus 2, we're going to group out to the cos here. So we'll get 2 sine 2x minus 1 and cos 2x. So what that means is sine 2x will equal to a half, because cos 2x cannot equal to 0, because otherwise this would be undefined, right? So we just state why we're not pursuing one of the paths further. So then we can so it's important to also like look at the restrictions in the domain and minimals and maximal domains and all that kind of stuff. So just keep that in mind as well. So then what we can do from here is kind of pursue that further, and we can now kind of look at actually finding solutions. So just kind of briefly to touch on finding solution. So we look at our triangle, it's our 2, 1, root 3 triangle. Once again, we're looking for this angle up here, so it'll be pi on 6th. Then we check which quadrant it's in, so it's going to be in quadrant 1 or in quadrant 2, right? And our domain is 0 to pi, but we'll have 2x will therefore equal to pi on 6 or 5 pi on 6, right? So therefore we'll have x will equal to pi on 12 and 5 pi on 12, right? So from there we can kind of take it from there, that 5 pi on 12 and pi on 12. But if it wasn't in the domain, we can always add or minus domains to really get it in there. Right, cool. Right, so that is circular functions. Let's talk and let's get a little bit about calculus. So the bread and butter calculus. Okay, so these are a couple things for your summary book first. So in your bound notes, you also should have the product rule, quotient rule, etc. But I personally, and I feel like a lot of math tutors and a lot of math teachers as well, don't really like the quotient rule, and I kind of agree because it requires more memorization and it's a bit slower as well. So what I would just turn it into is literally something which was, so if I had 1 over x, I would just turn it to x to the power of -1. Or if I had x squared over x plus 1, I would just turn it into x squared, x plus 1 to the power of -1. That's what I would prefer to do, but you know, by all means, if you like the quotient rule, you can always do the quotient rule. So these are some like questions. Essentially, you can just make this x to the power of a half, and then if we did that, when we try and differentiate, it would go a half x to the power of 1, a half minus 1, so it'd be a half x to the power of -1/2. So we'll just have 1 over 2 root x. And there's a lot of different ways you can write it. Just follow whatever form they ask you for, and if they don't ask you for a specific form, just simplify it as much as possible, but you can just leave it in whatever form you're comfortable with. Okay, these are some useful formulas that some of these are, so these ones aren't on the bound reference because it's kind of an extension of them because it combines them with chain rule, but I would say this one is definitely on your on your formula sheet, but I don't think the rest of these are. Oh, this one is the chain rule, and this one is on the formula sheet. I think the rest of them aren't on your formula sheet. This one comes up, so this is trying to differentiate a base which is not e of x. So when we try and differentiate a log which is non-natural base, when we try and differentiate an exponential which is non-natural base, and essentially where this actually comes from is we just make this e log, we change it so it's e log e, like a to the power of x, and then basically that just gives us e x log ea, and because x e log ea is just a, you know, it's just a whatchamacallit, it's just a constant number in the first place, therefore we can just kind of leave it from there and just kind of adventure out, because if we because e to the power of log e a x is equivalent just to ax, because the e and log e kind of cancel out. I would say this one is a super duper useful, especially formula for integration as well, because it helps you recognize stuff, and these are the formulas that we can use for all of the cos inverse and sine inverse and all that wondrous things. Cool. Okay, so let's go through this question together. So the first thing what we do is we know that sine inverse x over 2, so we can kind of do a bit of a chain rule thing here, or we can use the formula from before, but let's say we use the chain rule. So the chain rule, we have to diff the inside, so 2x, and then diff the outside, keeping the inside the same. So it's going to be 1 over root 1 minus x squared, right? So we can kind of see how that works, and if we look at the formula, it's going to be essentially the exact same thing as we've been doing here. So if you look at the formula, it's just going to be f dash x over that, right? Oh, whoopsies. So then what we can do is, what we'll get is this is going to be 2x over root 1 minus x to the power 4. And that's it. It simplifies something quite nice, doesn't it? Alright, implicit differentiation. This is something you'll also have to do. So implicit differentiation is essentially when we try to differentiate the y as well as the x simultaneously, because sometimes you can't break them apart. So you can't really make one thing the subject and the other thing, like, it's kind of like x squared plus y squared equals to 2. I feel like that's really, like x squared plus y squared equals to a or something. Like, that's a really common example, because you could rearrange for y, but you would get plus or minus. So it just makes everything a little bit more awkward. And implicit differentiation is actually relatively straightforward, and it's a better way to get around it. So what you do is you just differentiate everything as if y was the variable, and then after you do that, you just chuck a dy dx after every y that you differentiate. Importantly, if you differentiate something which is like x y squared, right? Really importantly, when you try and differentiate something like that, you must only add the dy dx when you actually differentiate the y component. So if we tried to diff something like that, the first part would be 1, right? Y squared, and then plus 2y x dy dx. So see how the dy dx only goes with the part when I actually differentiated the y, rather than this part. Because in this part, the y is kind of like, the y squared is just a inert type thing. It's not really participating in this process, but compared to this one where it's actually being differentiated. Cool. Alright, so let's talk a bit about related rates as well. It's often an application-y type of question that comes up not uncommonly, and gets even worse when we do differential equations. So what we want to do is make sure we know the information in the question. Particularly units are really important in any type of application question. And you can also talk about the direction of the gradient as well. So then you want to say to yourselves, so how I like to think of it is, what do I have? So this is, what do I have? What do I want? And what am I missing? Right, so what do I have? What do I want? What am I missing? And then I find what I'm missing, right? So I answered this question, and then that gives me what I want from an equation, and then I can kind of answer it in however many units I want. So those are my 3 questions. What do I have? What do I want? And what am I missing to get what I want, essentially? And you can write out the formula and then substitute the answers as appropriate. Okay, so in terms of parametric differentiation, it's literally the same as related rates. It's just the dy, like it's just chain rule. So dy dx will equal to dy dt times dt dx. It's a bit of dodgy maths, but essentially if you look at the denominator and the numerator and try to work those out together, if they cross out, then they are cancelled out and you can kind of combine the two together. It's a bit of dodgy maths though. Definitely don't actually draw lines through them, just write it out. And if you can see it, then it should cancel out. Alrighty, so let's go through this question together. Water is draining from a cone-shaped funnel at a constant rate of 600 centimeters cubed per minute. The cone has a height of 50 and a radius of 10. Let h be the depth of the water in the funnel at time t. The rate of decrease of h in centimeters is given by. So the first thing, that was a lot of information, right? We don't really care what's happening, so we know that it's draining from the funnel, so we know that it should be negative, right? So right away we know that dv dt is going to equal to negative 600. So that's the information we can glean from there. It has a height of 50 and a radius of 10. Okay, h be the depth of water in the funnel at any time. So this is h. Oh, sorry. That's h, right? And we want the rate of decrease of h. Right. So we want dh dt. So this is what we have. This is what we want. And if we write out an equation, so dh dt is going to be equivalent to dh dv times dv dt, right? So what we're missing is dh dv. Now, how can we get dHdV? So what's the relationship between the height and the volume of a cone? We know that the height and the volume of a cone, we get that V will equal to 1/3 pi r squared h. It's also really useful to have all of the equations and stuff kind of combined into to make sure you have like geometric equations. So stuff for cones, circles, spheres, and 2D shapes as well in your bound reference, because a particular spec, it uses a lot of shapes and like throughout their content. So in calculus, vectors, complex numbers, just doing basic linear stuff as well. Lots of shapes, and a lot of their proofs involve shapes as well. So it's really useful to have that basis. And because you learn the cosine and the sine rule in 1-2, they kind of use that as implied knowledge. So it's important for you to have those formulas and stuff in your bound reference, because it sometimes does make your life a little bit easier. Cool. So what we can tell from there is we're missing an r variable, and once you do this once, you'll probably never forget it. So what you use is similar triangles. So we know that this is 50 and this is 10. We also know this is r and this is h. So why these are similar is because they share an angle right down there, share this angle, share this angle, and share this angle, right? Because these two lines are parallel. So they share all of those angles in there, so therefore they're similar, right? So therefore what we can do from there is say h over r will equal to 50 over 10. So therefore you'll get that h will equal to 5r. So what we can get from there therefore is that we can sub that back in. So we'll get this is 1/3 pi 5r times r squared. So we'll get this is going to be 5/3 pi r cubed. Okay, so that's what V. Oopsies, we put it in the wrong one, didn't we? Let's rewrite that again. Got too excited, made everything in terms of r. So we need everything in terms of h because we're trying to find h, aren't we? So we need to find what in order to find dHdV, we need actually in terms of h rather than in terms of v. I mean in terms of r, so we can actually find it. So therefore r over h will be equal to 10 over 50, so r will equal to 1/5 h. So therefore when we have this, we'll have this as 3rd pi 1/5 h squared times h. So what we'll get from there is v will be equivalent to 1/75 pi h cubed. So what we want is dHdV, so we need dV dH first, which will give us 1/25 pi h squared, and then when we put that back into here, it'll now just be 25 over pi h squared times by, so that will be our dHdV. Now if we want our dHdt now, it's going to just be 25 over pi h squared times my negative 600. So it will be negative 600, so 6 times my 25 would be 150, right? And because we're looking for the rate of decrease, so we're looking for the rate of decrease, so that's 150, 150, and then 0, 0. So really the only answer which is looking appetizing is that one there. And we can see that the pi over h squared is at the bottom, so that looks good. These don't involve anything, so right away you can probably roll out the other options. But it's the rate of decrease, that's why the negative is gone. Okay, have a drink of water. Okay. Alright. Let's move on to second derivatives. So second derivatives are also quite useful. All we have to do is just literally differentiate another time, and it tells you how much the gradient is increasing or decreasing. So it's useful to find out where, like, if the turning points are maximums or minimums, because that kind of tells you, or if there's stationary points of inflection. Basically, if you have a double derivative equaling to 0, what that actually tells you is that there is a point of inflection there, definitely, because the gradient isn't even increasing at that point, so you know that it's completely flat. But the problem is we don't really know whether it's a point of inflection or a stationary point of inflection. That's why we have to kind of look back at f of x to be sure. Okay, so in terms of concavity, we find that out using the second derivative, because remember, that's what tells us whether the gradient is increasing or decreasing, and that's what concavity is, right? So when it's concaving up, the gradient is increasing, and when it's concaving down, the gradient is increasingly negative, or otherwise known as decreasing. So if we look at here, right, it's concaving up and then concaving down. So you can kind of see where it's going from there. And the thing is that it's not always corresponding to, like, so this one, right? For example, here, right? This part is concaving down. The reason why it's concaving down, even though it looks like it's positive, is because the gradient is higher here in terms of positive numbers than it is up here. So even though this is all positive, it's decreasing in terms of its actual gradient, right? Because it goes from, let's say, positive 20 to positive 5. And the same thing here. Even though it looks like there is a change of gradient across there, which there is, but in here, it's actually concaving up because it's increasingly getting positive, because it was really negative before and it's increasingly getting positive over that slope. So in terms of the second derivative, concave up is smile, as the increasing gradient as x increases, negative gradient concave down, decreasing gradient as x increases. So it's really easy to get tricked by saying, oh, the gradient looks positive or the gradient looks negative, but just think of what the gradient is at the start and then what is actually happening to the gradient as it goes along. Okay, so when we do the second derivative test, what we use that is to tell whether we have a minimum, maximum point of inflection or stationary point of inflection. And what we actually do is we want to test the nature by the stationary point by just subbing it in. You essentially just find what the second derivative is and then sub it in. So if it's positive, it's a local min, and that's because we know that it would be increasing, right? The gradient is increasing over that position. So that means that it's a concave up position. So it's gradually, it's from something that's negative becoming more and more positive. So it's a local min. If it's negative, it's a local max, because it's going from something which is really positive, right, becoming less and less positive, and eventually gets to 0, becomes even less positive, and becomes eventually negative. So if f of x equals to 0, we need to find out whether it's a point of inflection or a stationary point of inflection, right? So we can just sub it into the first derivative again to find it out. If f dash of x also equal to 0, then it's a stationary point of inflection. If it doesn't equal 0, then it's just a point of inflection. So if you really want to talk about point of inflections, you can talk about how it changes signs, like either side of the point of inflection. So because essentially in terms of a point of inflection, right, you're going from something which is positive, right? So you're going positive, really positive. So it's going something, really, it's the secondary derivative is becoming negative, right? Because we came from something which was really positive, became less positive, and then it moves up here, becomes like negative or 0 here, and then doesn't become negative, it just becomes 0 here, like the actual second derivative would be negative here because it's becoming less and less positive here, right? So the actual section here is less and less positive, so therefore it's negative. So the second derivative is negative here. And then once it gets to here, right, it starts from something which is just 0 and then becomes more and more positive. So we'll have f dash dash x is bigger than 0. And that fully shows that you actually have a point of inflection there. Okay, amazing. So then let's just talk about how we have the second and first derivative kind of interacting with each other. So essentially, in terms of first and second derivative, what we have is the relationship evidently between the two is that we have f dash dash x is when we do d of dx, and we can also talk about other way around is the integration of that, so whatever it is dx. What each of these kind of mean is, so this will tell you the point, this will tell you the gradient, and this one will tell you the gradient of the gradient. So an important thing is that if you're looking for stationary points in that one and you go to the second derivative, it won't tell you the nature of the stationary points in the derivative, right? You actually need to go one step further to find the third derivative after that. Right, so let's kind of just go through how they interact with each other now here. So essentially the position of each thing should be, the same. So let's draw out a table to talk about what's going on here. So let's draw out our table. So this is our f dash dash of x, and this is our f of x. So we can draw out our table to kind of talk about what's going on. Alright, so we can say, alright, let's do f dash dash of x is bigger than 0, f dash dash x is smaller than 0, and f dash dash x is equal to 0. So if we have f of x equaling, then we have f dash of x bigger than 0, f dash of x smaller than 0, f dash of x equaling to 0, right? So in this one, the gradient, so this is positive gradient, negative gradient, no gradient, otherwise known as a stationary point. This one is gradient is increasing, gradient is decreasing, gradient isn't doing anything. Okay, cool. So when we look at this, right, what's happening when the gradient is increasing, when the points are increasing and the gradient is increasing, what happens is we'll have something which is in a section literally like this, right? So it'll be like that, because the gradient will be starting from something which is normal and then it'll be getting bigger and bigger and bigger, right? When the gradient is decreasing and when the gradient is smaller than 0, and then so when it starts as something negative and then the gradient is increasing, that's when we have our smiley face kind of position. But I guess we have to note that in between here, that's where it equals to 0, right? So we'll just rub out the other side of it. But this is like, this side is this side of the smiley face, and this one is this side of the smiley face. Let me just make sure to rub it out so that we don't get confused. So in terms of what's happening, we have this one is equaling this side of the smiley face, and this one's this side of the smiley face, right? So that's kind of, if we look at like, if we did a gradient along there, we would say that that's what's happening at those points, right? And then here, this one is just the base of the smiley face. So right here, that's where we're looking at. So that's why we have, go away. Just try to make this go away so you can see the bottom bar. Normally it goes away when you... Okay, that's alright. Hopefully it goes away by itself. If not, we'll look at it in another slide. Alright, so that's why when we have this kind of like, if we kind of put all of those together, we can kind of see how that forms a turning point type thing. So when it's positive, it's always going to form the local minimum turning point. So we have a smile. Okay, so when we have a negative one, so when the gradient is bigger than 0 and it was originally positive, that's going to be this arm of the equation, right? Because it's positive, 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 getting less positive. Now this one's going to be this one, right? Because it was negative, started as negative, became even more negative. So this part is going to be this top part here. So it's going to be the frown part of it. Right. So what if f dash dash x is equal to 0 and f of x is bigger than 0? So what this is actually happening here is what we have is a non-stationary point of inflection. So what that actually means is that we have a point of inflection, right? But instead of something being horizontal, like you can see here, where the gradient isn't changing, it's kind of on an angle. So we can see that the gradient is still changing. We can see that the gradient is still positive at that point. Sorry, not changing. The gradient is still positive at that point, but it's just unchanging, right? Because it's the same slope. It's kind of like if we had a line in between. If that part's like kind of a linear line. And the same thing here. It's like having this on a slope. So you can see that the gradient is still not zero, right? Because it's not flat. But we can see that the gradient is negative, but it's just becoming, so it goes negative, 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 becomes less negative at that point, right? So this part would be corresponding to here. So it started from negative, became less and less negative, got to a non-stationary point of inflection, stayed at that negativity, and then became more negative after that. So it kind of moved on to this one. So we can see how the sign is changing. Alright, so then if we equal to 0, that's when we're going to have our stationary point of inflection like that. So we have a flat gradient. Gradient goes from something which was positive becoming negative, right? So we can see that this one corresponds to this, and then we have this side which corresponds to this. So we can see once again the sign is changing across that. Cool, amazing. So that's the different interactions. I would recommend to draw this table in your own time as well to kind of have a diagram of what's going on. Alright, so let's talk about how we do this. So if f dash of x is bigger than 0 and f dash dash of x is, so second derivative is smaller than 0 for all of x over a given part of the domain of a function f, then the graph of the function over this part of the domain would be the curve which. So what this implies to us is that the gradient is decreasing and what this applies to us is that the gradient is positive. So over this part of the domain the curve would be, so because the gradient is positive, that means that the curve is increasing, right? So right away we can say, okay, the curve is increasing in some manner or form. So that means that we can use this answer, or this answer. And then we know that the gradient is decreasing. So it's going to be decreasing across this. And the increasing x is kind of just used to say that's what's happening as we go from left to right. So we want to say that the gradient is decreasing, but the actual graph itself is increasing, right? So f dash of x means strictly increasing, and then double second derivative means concave down. So therefore we would get C here, because we can see that the graph in this section will look something like this. If we kind of go back to our previous question here, you can kind of see it's going to be this case, right? F dash of x bigger than 0, f dash of x being smaller than 0. Yeah, so you can see gradient is increasing, and then gradient, so the curve is increasing and the gradient is decreasing, right? Cool. Alright, so in terms of your summary book, what you should have in your summary book is implicit differentiation. If you see a y, differentiate, but just shove dy dx after. In terms of points of inflection, concavity, that type of thing, we can use that to verify turning points like the direction of the gradient. Maybe. Sorry, I'm just trying to get rid of this thing here. So that you can actually see the bottom of the, maybe I'll just do this really quickly. And then start it again. Sorry for this. Just want to make sure you can actually see the bottom part as well. Cool. So in terms of this, we can differentiate the y, but then shove the dy dx after. In terms of points of inflection and concavity, we can use that to identify the direction of the turning point / the direction of the gradient. So if it's bigger than 0, it's a local min, because once again, really, so it's negative, 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 comes to become more 0 and then becomes positive over that direction. Then we have local maxes, so positive becomes less and less positive, and then eventually becomes negative. If it's equal to 0 and f dash of x, if the double derivative is equal to 0, and so it should be the other way around. So if the double derivative, why is it not working? So if the double derivative is equal to 0, right, and the gradient is not equal to 0, that's a point of inflection. If the double derivative is equal to 0 and the gradient equals 0, then it's a stationary point of inflection. Okay. In terms of related rates, we can look at the units in the question, make sure to have a look at what they give you and what to use, and just use the chain rule / parametric equations. So use that equation right there. Okay, so in terms of antiderivative graphs, this is often a really common question in exam too that you might have to explore. And importantly, the main thing to do is just to remember that the x-intercepts will show the stationary points, right? So if you're going from something which is a derivative, diff, to its original, the x-intercept should show the stationary points, and anything above or below the gradient shows the direction of the gradient. So you can kind of do a bit of a gradient table using that. Ooh. So let's go through this question together. It might be a little bit hard to see, but essentially it's asking you to, so for the sure the following could be the, so part of the graph of the derivative of the function above, the function f is shown above. So this is the derivative of the function, right? And they want which of the following could be the graph of the function. So they want the graph of the function, right? So this is the derivative and they want the graph of the function. All right, so right away we know that these are going to be special points. Then we can kind of, I just do this. So I go, this is negative, positive, positive, negative, right? So therefore I know that my thing is going to go negative, positive, up, and then back to here. I don't really care what's happening up there. Like it's probably a like one of those non-stationary points of inflection, but I just, because if we think of like the double derivative of this, that would be an x-intercept at that point, right? Because it's a special point at that point. So therefore it would be like some type of wiggly thing happening there, but it would just, we just note that in our equation. Okay, so we're going from positive and then we become normal and then become negative again. So that's the general shape I'm going to be looking for there, and that's the shape I want out of that. So this shows the derivative, which of the following could show the graph of the function. So I want a minimum and then a maximum, so we can see that this one kind of shows what we need. So the graph of this one, I think this kind of looks like a non-stationary point of inflection, but this doesn't look like a stationary point of inflection. So we could be having something, you know, a bit, oh, sorry, this is positive, isn't it? So it actually goes like this instead. So this could be something quite interesting happening here. So we want it kind of to go up, and we can see that it's a positive point of inflection there. So it wouldn't be that one, and it wouldn't be that one, and we just ruled out that it wouldn't be that one as well because I didn't write the correct direction there, but plus positive and positive. So therefore this one, right, this is a non-stationary point of inflection because you can see that the gradient isn't flat there. The gradient's only flat in that one, so it in fact would be this one instead. Yeah. So this one, like the shape of this one would more correspond to what's happening here rather than what's happening here. Cool. Alright. Okay, integration. So integration is just a reverse of differentiation, just like it's the inverse function of differentiation essentially. So what we're doing is, important thing is you know what's going on, and just make sure that you have like a and b as the upper and lower bounds. Remember, it's going to be b minus a, so make sure to keep it in the correct order, and make sure to put the dx at the end. That's really important because if you leave that off, you won't get the mark for it, unfortunately. Okay, in terms of summary books, these are the formulas that you'll have on your formula sheet. It's also useful, just like with the formulas that we had for differentiation, just to write a couple of the formulas which might be a little bit more trickier to kind of talk about. Another thing that you can do is when we're looking at this, remember that for the log, you'll always have that like modulus outside. So it's really important that we know to reject the modulus, and it's basically based on what the values of x can be for that function, and often it will tell you, and then you can just kind of guess from there, or not guess, but like kind of reason from there which side you have to take. And this is just a slide to say make sure you don't forget the plus c, because that's really important, because if you forget the plus c, they won't give you the mark. The only exception to that is like the thing of an versus the derivative. The antiderivative. If they say the antiderivative, you must put the plus c. If they say an antiderivative, technically plus c could be 0, right? So you could technically also just put no plus c and it would still be the same thing. But I would say you can just always put the plus c to be safe, because even with an derivative, in an antiderivative, putting the plus c won't make you be wrong. Cool. Okay, let's talk about the process of integration by substitution. So there's a number of, let's say, tools that we have in our belt for integration. So there's substitution, we have by parts, we have by recognition, which is kind of the sister to by parts, and then we have also, we'll have the integration like using our like y-axis as well in Spec, and then we'll have integration using our circular functions, which is kind of like a special part of the integration by substitution, because circular functions can be funky, and also circular functions, like using the circular function rules as well, can be really helpful. Cool. All right. So let u is often very helpful in the terms of looking at like polynomials. So what we want to do is step down in power, okay? So the u will always be the one which is bigger, and the du dx will always be the one which is smaller. And it's okay if like you kind of miss which one's which. Over with practice, you will get better at kind of identifying which one you need to substitute and which one is the du dx component. What I look for in a question when I consider using this is, can I see the function and can I see the derivative in the same equation, and can I use that to my advantage? In a question where they have a denominator which is a function, often the denominator will be the u, so that kind of gives it away a little bit. In terms of the steps, so we just let one of the parts equal to u, we need to find the du dx, and then we need to rearrange to kind of plop that into the equation as well. And then we put that in, so we convert the term. So if you have a definite integral, what that means is you don't have to convert back to x. But if you have a indefinite integral, what that means is you have to convert back to x, because remember they want it in terms of x, not u. But that's, we'll talk about that when there's a question on it. But essentially, if you had like something that was in terms of x, so something in terms of x, you'd have to convert back to x. But if you have like terminals, right, so definite integral, you don't not need to convert, because you can just sub in the terminals and it's a like it will be a number, right? And even if you convert back to x and try to sub in the number, it'd be the same thing. So you can just do that straight, but you need to convert back for this one. And then you can just solve for u and then sub the original back in. So you put in the u's, give yourself an integration which is actually easy to do, and then you can kind of put u and x back in after that. A special one is when we have like a linear. So what you do is you just make x equal to whatever the linear thing is, and then you make du dx equal to 1, because 1 times anything is just going to be the anything, so we can always use that, which is helpful, right? Because if you have something like root 4 minus x, we can definitely use that there, because we can say u equals to 4 minus x, and du dx just equals to 1. And now suddenly you have this, you've simplified this just to root u instead. So it's really nice. Cool. Alright, so let's talk about this question. I'll pop this question into the chat because I think it's a really good question to actually have a go at together. And I might give you maybe like, I don't know, like 10 seconds to kind of think about on your own of what you might do here, because I think it's really important for this one, and then because it tells you the substitution as well. So I might give you 20 seconds to just have a think what you might do and what you might consider. Okay, so hopefully you had a bit of a think about the general steps you might take and what you might do here. So it tells you the substitution straight away, which is actually really nice of them. So they want you to evaluate this. So because we're letting x equal to 2 sine u, we can kind of substitute that in. So we'll have, let's just kind of work out what this is first. So root of 4 minus 2 sine u squared, right? So what that's going to be is it's just going to be root of 4 minus 4 sine squared u. And this will look familiar to you because remember the cos squared x plus sine squared x will equal to 1. So if we kind of rearrange that and put a u in, we'll know that cos squared u will equal to 1 minus sine squared u, right? And we can just take out the 4 at the front there. So we're just going to get root 4 of cos squared u here, which means we're just going to get 2 cos u. So because this is just the positive root of it, we don't need to be concerned about the plus or minus, because it's not to say, it's not saying that x squared equal to cos squared u. It's literally rooting whatever it has in there, right? Just like the root of 4 squared is just going to be 4 rather than plus or minus 4, because the root is always going to give you the positive result. Okay, so we get 2 cos u, right? Okay, so then in terms of our du dx, what we're going to get is that this is going to be so in terms of our 2 sine u, right, we're just going to derive that, and the derivative of sine u is just cos, let me just put, because we have it in terms of u right now, so I'm just going to rearrange first before we jump ahead to that. So our x is going to equal to our 2 sine u, so therefore our dx du rather than our du dx is actually going to be equivalent to 2 cos u, right? Because the derivative of sine is just going to be cos. So then what we can do from there is actually kind of look into it a little bit further. So now we know our du dx is now going to be 1 over 2 cos u. Yeah? Okay. So then when we try and actually put it in and put it into the equation, right? Because we've gone from something which was we've gone from something which was 2 cos u before, and now we're going to try to make it to look like what we want to work with, right? So in terms of trying to find du, let's put this in now. So we'll say the antiderivative of 4 minus x squared, right, dx is also going to, so we don't need to sub in the terminals for this one, fortunately, so that we don't need to explore it too much. So what we can actually do here is, because we have this dx kind of component here, what we want to do is, it's just like when you it's just like when when you're when we try to do the parametric differentiation of the dx over du will be equivalent to our dx dt times our dt du. It's just like that. So what we're trying to do here is something quite similar, except we want our x component to be at the top, right? So when we're trying to do this, what we can try and do is we'll put this in, so we have this 4 minus x, right? Because we'll have our we'll have our cos component here. So we'll have, this is going to be equivalent to 2 cos u, right, dx. And then we need to take care of our dx component as well, and we would need to care for what's kind of going on with that component. So if we kind of look up to here and try and figure out what's going on, we can know that we have our x equaling to our 2 sine u, and therefore we'll have our dx du equaling to this equation. So what we can apply here to kind of get rid of that is instead go back to this one. Oh, that's not, sorry. Let me go back to the pen. Cool. Alright, so then we have our dx du here, and then what we're going to kind of substitute in is our u component. So what you're trying to do is actually make your du component the subject here, because what you want to do is you want to get rid of the dx component, right? So what you're going to do here is instead of putting this in, you're going to rewrite this as dx equals to 2 cos du. Now that's a bit of dodgy maths, so like I think that it's better if you can write it without writing this statement, but if this statement helps make it more clear, you can always write it and then just rub it out. So then what you do is you can now put that in, right? Because now I'm going to write that. Oh, why'd that do that? Oh, sorry. Just need to rub it out. So I just need to put that in, so that will be cos du, so we can put that into there, so that will be 2 cos u du. So then from there onwards we can kind of make it a bit simpler, so it'll be equal to equivalent to 4 cos squared u du. And then we can kind of utilize the rules that we know. So we know that cos 2x is equivalent to 1 minus cos squared x, right? So we can kind of utilize this rule over here. So we can say that therefore we'll have that cos squared u will just equal to, 2 cos. So it will just equal to 1/2 of 1 minus cos 2x, right? So when we kind of put that across, we'll have that's going to be 1 minus our cos 2x. So therefore we can kind of replace it with 1 plus our cos 2x. And therefore we can kind of replace it with what we have so far. X minus 1. So we can kind of replace it with this. So we'll have this is going to, there's not enough space. So it's going to be equivalent to just saying that it's 4 times 1/2 of cos 2x dx, right? So then we can kind of simplify that and just kind of simplify that down. So it's just going to be 2 cos 2x dx, right? Or 2 cos plus 2 dx. This is getting really messy. I'm going to just rub, I'm just going to rub all of this out and then rewrite, because there's not enough space for this, all of this to be on the same page. Okay, amazing, cool. All right, sorry about that. There's just not enough space and everything's kind of getting munched together. All right, so we kind of ended up with saying that this was equivalent to 4 cos squared u dx, du, sorry. And therefore from there we can kind of sub in our thing that we were talking about up here. So it's going to be equivalent to 4 times 1/2 1 plus cos squared 2u du. Okay, that's so much better that we can have space and actually see the working out. So 2 plus 2 cos squared 2u du. So what we're going to get from there is 2u plus, so when we anti-differentiate for cos, right? So essentially it just turns into sine, but because there's a coefficient out the front there, the 2 kind of gets taken away so that it reduces itself. So when we go from something like cos 2u and we try and differentiate that, that becomes 2, like negative 2 sine 2u, right? So we don't really need to worry about the negative too much, but for this one, we just know that basically the coefficient comes out. So we can kind of divide by the coefficient, and that's perfect. So we'll just end up with cos 2u, sine 2u du. Alright, cool. So now we have to substitute back the x in. So our x was 2, our x would have been x over 2 equals to sine u, so our u would have equaled to sine inverse x over 2, right? So we're dealing with this sine inverse x over 2, so what we're going to get here is 2 sine inverse x over 2 plus our sine inverse, our sine of 2 times our sine inverse of 2 over u. Sine inverse x over 2. Alright, so that's what kind of we can get from there. That's going to be our overall equation. So then we also need to add the plus c, because if we don't add the plus c, this will all be for naught and we won't get the correct answer. So after we do this, then we can kind of figure out what's going on from that. So this next step isn't really more calculus stuff, it's more kind of just like circular function stuff, and I guess it's a good thing to talk about and talk about how we can rearrange this. So let's kind of disregard the first part for now and we can kind of take it all along the end. So let's just kind of consider this part first. So we substitute that in. So what we do is we can just turn that into 2 sine of our inside angle, so sine inverse x over 2 and cos of sine inverse x over 2. Right? Cool. Right, let's rub it out all one more time. So that we, let's erase all ink on slide. Actually, that's quite smart. Cool. Alright, and then let's do this one more page of writing for this. So this is a really long question. If you got this question, it'd probably be worth like 5 or 6 marks, honestly. And I think it would be broken up a little bit more into its individual parts. But so far that we've gotten that this is equivalent just to 2 sine inverse. Oh my gosh, I can't write. Let me try that again. Okay, so ink, and then let's go to pen. Alright, so it's going to be equivalent to 2 sine inverse x over 2, and then we said plus, it was sine 2, it was 2 sine, and then it was sine 2 of sine inverse x over 2, like that. Cool. Alright, so let's focus on this second segment right here, what the sine inverse x over 2 component equals to. So if we focus on what this is equivalent to, this would be equivalent, like we were talking about, to sine inverse x over 2, so 2 of that times by cos of sine inverse x over 2. Now, we can apply our knowledge here of what sine inverse x over 2 is. So sine, once again, is opposite over adjacent. So if we made opposite here and adjacent here, we would get that this is going to just be x squared minus, wrong way around, 2 here, x over here. We would get that this one is just going to be 4 minus x squared, right, as the kind of the adjacent side to the angle up here. Alright, so therefore we can kind of rewrite this whole thing as 2 sine inverse x over 2 plus of our, so we'll have our 2 of our sine inverse x over 2. So we'll have our 2x over 2, right, because it's the sine of the sine inverse, right? And then we'll also have, so we have plus c at the end here. Plus c at the end here. And then we'll also have this component as well, which is going to be our root 4 minus x squared over 2, right? So then if we kind of write it out and simplify it and make it all in all, we'll end up with 2 sine inverse x over 2 plus x root 4 minus x squared over 2. Okay, and then plus c. Make sure to add the plus c's. Alrighty, cool. Sorry, that was a really complicated question, but I think it's really worth doing. So just kind of note that question down and put it into your bound notes or have it somewhere to have and peruse. Alright, this one is a lot more straightforward, and essentially all we need to do is just so we need to recognize which one has the higher power and what's going on. So often the one included in the function is the one we want to let u. So we have let u equals to x squared, so du dx will just equal to 2x. So we can kind of manipulate this into 1/2 2x sine x squared dx. So what we're going to get here is it's going to just be a half, right, of sine u, and then we're also going to have du dx, right, because we're replacing the 2x with du dx times bx, and you can see those two cancel out, right? So therefore what we're going to get here is it's going to be a half of sine u du, which is just, so remember cos goes to negative sine, so if we anti-differentiate sine, it'll go to negative cos, so we'll have a half negative cos u, right, plus c, and then we can just substitute that back in. So we'll have negative a half of cos 2x plus c. Yeah, that's right, cos, not 2x, cos x squared. Let me rub that out. Cos x squared plus c. Cool. Awesome. Alright. Okay, so these are some partial fraction laws. I won't talk you through them because you can read. So just make sure you have these somewhere in your notes. That's really the only thing I wanted to highlight on this slide. Make sure you have it somewhere on your notes because it's really important for you to read and know how to do these. Okay, integration with trig, we've already done a little bit of this already, but essentially if you have even or odd powers, so what you want to do is essentially when you look at a trig thing with sine and cos all together, what you want to look for is which one has the bigger power, and you want to make everything the same base, and you also want to look for which one has the bigger power as well, and then you can use that substitution with u to kind of get rid of it. So we split the power, we can use sine squared plus cos squared equals to 1, we can use double angle formulas, etc. And then we make 1 equal to let u equal to the trig of the opposite trig of the odd power, or the one that has more powers, and then you can kind of substitute whatever you have in for the sine x or whatever, and then you can just solve. Cool. Alright, if we have even powers, what you do is you just use these formulas. So you're using like cos squared x sine squared sine 2x and sine kind of these types of formulas. So using all these ones are the double angle formulas, right? Oh, sorry, these 3 are the double angle formulas, and this one kind of just comes from the cos squared x plus sine squared x formula, so we can use that as well. Equals sine squared x equals to 1. So those are the formulas that it's derived from. Alright, let's go through this question. So first of all, we need this to be the same base, so what we're going to change this into is 2 sine 2x cos 2x cos 2x, right, dx. And then what we're going to get is sine 2x cos squared 2x dx. Alright, so we see that this one is alone and this one has squared power. So we have odd powers here if we added them all together. So what we're going to do is we can let u equal to cos 2x, right? Because this one is the one that looks like has more power on it, and this is lonely by itself, so we're pretty happy to just do that. So therefore du dx is going to equal to negative 2 sine 2x, right? We have the 2 already there, so we're happy with that. And then we just need a negative, so we can pop a negative out the front, right? And then we'll just have cos squared, so that's u squared du dx, so our negative 2 sine 2x times our dx, right? So that's going to just give us negative u squared du, which is going to give us that's going to be equivalent to negative 1/3 u cubed plus c, which is equivalent also just to saying negative 1/3 of cos cubed 3x plus c. And just as a kind of a quick note to also note this in your thing, just for anybody who has TN, there's shortcuts for both calculators, but for anybody who has the TN Inspire, in terms of like the calculator kind of hacks for it, if you just go to, so if we pretended to type in this one, so if you kind of go to shift and then plus, it will give you the anti-differentiation one, and by doing that you're able to just pop in your equation, so you don't have to kind of go menu blah blah to kind of get your equation that you're trying to do, right? So from there you can kind of, so it was a lot quicker and we can kind of pop that into our calculator like that. Right, so then what we can kind of do after that is, so we see that this gives us our kind of our x squared component, right? So what we'll have is this, so we'll have this like kind of this component of what we're trying to do. So you can kind of change what that looks like as well. So in terms of our cos cubed x, we can kind of rearrange that into like a bigger formula as well. It's kind of up to you what you want to do, but you can just leave it like that as well. It's kind of up to you what you want to do from there. Okay, cool. So then integration by parts. When we do integration by parts, there's kind of two ways to do it. So there's the by parts way, or there's the by recognition way. By parts was only introduced this year, and it's essentially kind of the integration form of the product rule. So what you do is you use this thing like, use that kind of like acronym. So we have log, inverse, circular functions, algebraic, trig, and then we have exponentials, and those are kind of the order of the functions that we go with. And you make one of them a function which you're going to differentiate, and you make the other one the one that you integrate, and then you kind of just use this formula and sub that in. Okay, for integration by part recognition, so this is kind of a simpler type of one, I would say, is they actually ask you to differentiate it first, and then you integrate based on the differentiation you already have. Cool, so let's talk about it. So they want us to show that this is equivalent to this, and then hence evaluate the area enclosed by this graph and the two lines. So if we have f dash of x, and that's going to be equivalent to, so we diff the first, keep the second, so I'm just going to say that's 3 tan inverse 2x, right? And then diff the second, keep the first, so I'm going to say that's going to be 3x, and then it's going to be, so when we're anti-differentiating these, remember we just keep so we differentiate the top, so that will be 2, right? And then it will be plus 1 2x squared. So when we simplify that out, we'll get that that's 3 tan inverse 2x plus 6x over 1 plus 4x squared, as we need, right? Cool. Alright, so then we want to evaluate the area enclosed by this graph and the lines like this. So we already know that this, right, is the kind of the inverse function of what this is the derivative that we're working with. So straight away we can say root 3 over 2 to 1/2 of this 3 tan inverse 2x plus 6x 1 over plus 4x squared dx is going to be equivalent to 3x tan inverse 2x. Root 3 on 2 and 1/2, right? Cool. Alright, so then the next thing we have to move over is this chunk of thing, right? So we're going to move that over, and we're going to say that's root 3 on 2 and 1/2, 3 tan inverse 2x dx is equivalent to 3x tan inverse 2x root 3 on 2, 1/2, and then we can put that on there as well, so minus root 3 on 2, 1/2, 6x 1 plus 4x squared dx. Cool. So in terms of 6, the integral of 6x 1 over 4x dx, what that is actually equivalent to is if we let 1 plus 4x equal to u, your du dx would have been 8x, right? So therefore we can kind of substitute that back in so that this is 8x. So essentially all we needed to do to manipulate this is we can change this top part to 8x, and we need to divide it by 4 and times it by 3. So 3 over 4. So then we can kind of change the terminals as well, so we don't have to come backwards. And when we substitute the terminals in, so when we have root 3, we'll have, this is going to be root 3 on 2 squared, so that's going to just be 3 on 4, right? 3 on 4 times 4 is just going to be 3. 3 plus 1 is going to be 4, so we'll have, this is going to be 4 at the top. We'll have 4, that's going to be 4 at the top there. And then when we do a half as well, so a half put into there is just going to be 1, right? 1 plus 1 is just 2. So essentially we're going to just end up with something like this. So we can kind of substitute that across and divide by 3 at the end, but we can divide everything at the end, like at the very, very end. So root 3 over 2, a half, tan inverse 2x dx is going to be equivalent to 1/3 of whatever this is. So we can also start substituting this in. So root 3 over 2, and tan inverse of root 3 is if we use our triangle. So that's root 3, that's 2, that's 1. So tan inverse of root 3 would be pi on 3. So it's going to be 3 root 3. Also, it's going to be root 3 on root 3 pi on 2, because root 3 on 3. So we'll have, this is going to be root 3 on 2 times pi on 3, right? Then we're going to have minus of a half going into that, so that's 3 over 2. And a half going into that, that's tan inverse 1, which is pi on 4. And then we're going to have here minus of our function that we're doing before. So we said that's 4 and 1. And we've replaced, we kind of took care of the top part. And we have 3 on 4 out the front here. And then we can kind of put in the stuff we had from before. So that's going to be 1 over u du, right? Okay, so we're going to end up with a log here. I'm just going to, I think I'll rub out this first section here to kind of talk about, to give us a little bit of space. So like that, and then if we want to talk about what's happening, oh, wrong one. So if we want to kind of talk about what's happening here, so this times that would just give you, so we'll get that the answer is going to be equivalent to, because the 3 can also be distributed across, right? So we're going to get that here, we'll kind of distribute the 3 across. So we'll get its root 3 pi on 2 minus pi on 8 plus, or minus this part, minus 1/4 of u, which is log e u, right, for 1. So that's going to be equivalent to saying, so if we times that by 4, so that'll be 4 root 3 pi minus 1 over, or minus pi, all over 8 minus 1/4 of log e, so that's 4, log e4 minus log e1. Log e1 is just 0, so it's just log e4. Right? Okay, cool. And then we make sure to do the plus c. We could probably put plus c's all throughout, but yeah, you can just put the plus c's at the end as well. Okay, amazing. Alright, this one's using Lyautey, so we can first see that it's inverse circular function, and the other one we can just say this is one of the functions, so f of x, we're going to say that's going to be equal to cos inverse 2x, and then we're going to say g of x is just equivalent to 1. So remember from the components that we needed before, we needed f of x, g dash of x, and we needed the integration of this. So that means that we need to find the kind of the derivatives of each first. So we find the derivatives, so if we find f dash of x, that's just going to be equivalent to 2 over root 1 minus 4x squared. And then our g of x, when we try and differentiate that, So we want to be getting a function, g dash of x equals to 1, right? Because that's the one that we want to integrate. So g of x would therefore equal to x. And we don't really need the plus c stuff here, just because we're actually putting it backwards and putting it forwards, and we're eventually going to kind of put the plus c at the end. So if we kind of look at what we want is the integration of this, which is, so the integration of our f of x times our g dash of x dx is going to be equivalent to our f of x times our g of x minus the integration of our g, was it g, I think it was g dash of x, yeah, so g of x times our f dash of x, right? Because that's the one that we're trying to do. So g dash of x, g of x, so it's kind of like how in the product rule, because it's g dash of x, f of x, plus f dash of x, g of x. So you just need every combination of those two. So this one had the dash, so this one doesn't have the dash, and this one's the f dash of x dx. Okay, so we can pop everything into here. So we will know that the integration of cos inverse of 2x dx is going to just be equivalent to f of x times g of x, which is just those two times together. So it'll be 2x over root 1 minus 4x squared minus the integration of g of x times f dash of x. So, sorry, that's f dash of x. So it's just cos inverse of x. So it's these two kind of combined together for the first one. So it's just going to be x cos inverse 2x. And then we're going to have our g, which is going to be just minus our g of x, which is our x, right? Times our f dash of x, which is going to be just be 2x over root 1 minus 4x squared dx. Once again, we can let u equal to 1 minus 4x squared, so du dx would have equaled to negative 8x. So what we can have here is we can minus that from a fourth. So we'll have a plus c at the end here. So we'll have x cos inverse 2x, and then we'll have our plus c component. So we'll have we'll have plus 1/8 actually, plus 1/4. Oh, yes, plus 1/4, right? Because the negative is kind of integrated into there. And we'll have du dx at the top, which will cancel out with the dx, and then we'll just be left with 1 over root u du. Right? So in terms of 1 over u root du, let's put out the 1/4. So that's going to be equivalent to u to the power of negative a half, which means that we need to times everything by 1 over 1/2. And then we need to also increase the power by 1. So that's going to be root u now. So it's a half root u, and then we have plus c at the end. And then all in all, what we're going to get is x cos inverse 2x. So that's times by 2, so plus 1/2 root u, which is root of 1 minus 4x squared plus c. Cool. Okie dokie. Alright, so in terms of substitutions, this is kind of like the summary page for them. Just remember to step down powers, and you can use the special case ones as well. And just remember all the formulas that can be used. And really importantly, have this somewhere in your notes, the kind of partial fraction stuff, and kind of this formula and have that formula on your notes somewhere as well for integration by parts. Alrighty. Okay, so in terms of areas under curves, what you want to do is it's always going to be the upper versus the lower, and in terms of the signed area, it's not the modulus, so it will be whatever this area is minus this area, and the actual area is going to be when we put like a modulus out the front here. So let's just kind of talk about the 3 different cases of if we're kind of considering graphs under curves. So what we're going to have here is we can have the first case, which is everything is above the axis, i.e. something like this, right? A to B. We can have things which are all below axis. So we can have something like this, where it's like that, and A to B. Or we can have something like where there's stuff above and below the axis, like this. So we have A and B. In this case, we can just integrate b to a f of x dx if we want the absolute area. For this one, what we want is we just negate it because it should be positive. So b to a f of x dx. Alternatively, you can also swap the terminals as well. It gives you the same effect. And this one, what we need to do is cut it at this point. Let's say that's x. So we'll say that's b to x, negative b to x, f of x dx, and then plus x to a, f of x dx. And that's going to give us the same thing. Cool, awesome. All right, so what about areas between curves? So same thing, we also have two types of things compared to the previous one, right? So what we'll have here is, if we look at these two ones, right? So there's no interchanging areas, which means we have something like this and then like that. And then we have here A and B, and that's our area that we're looking for in there. And in that case, we can just go b to a, f, let's say this top one is f of x and the bottom one is g of x. So that's just f of x minus g of x to give you the positive area. If there is interchanging areas, like something like this, and then we have, and we might, to make it even more interesting, let's say that's a, and then that point is b. So what we do here is we just need to kind of break it up into the sections. So top one's f of x, bottom one's g of x. So we break it up into this first section. We can break it up into like little sections. So we can start from left to right. So in this one, g of x is at the top. So g of x, right, minus f of x. And let's name these C, D. So it'll be g of x to f of x dx, and it'll be from C to A. And then we will plus our next one, so that's from D to C, and we'll have f of x minus g of x. And then we'll plus our last one, which is from B to D, and we can see that the g of x is once again at the top, so g of x minus f of x dx. Alright. Cool. Alright, so if you're finding the inverse area under the curve, what we're trying to do is like differentiate using the y-axis instead. So if we're differentiating something like a log, which doesn't have an antiderivative, what we can do is actually differentiate this section instead and then make a square and minus it from that. So it's another way that we can do it. So let's kind of talk about it using this log. So we have a graph of log 2x, right? Which means that we'll have something like this. So if we subbed in like 1 here, we would get that this is log e2. So if we tried to sub in a half, right? A half would give us log e1. So that's where it equals to 0. And we needed to find that because it's asking for the x-axis and it equals to 2. So you just need to find the intercept first. So it's from 2 to a half, and that's kind of the area that we're looking for. So what we're going to be going at here is now we also need to find out what log e2 corresponds to, and that will correspond to log e4. Now, we want to get this area here instead. So unlike an inverse function, we don't actually have to make it an inverse function. All we have to do is just rearrange for this. So it'll be e to the y equals to 2x, and then x equals to 1/2 e to the y, right? So we can kind of see that's going to be what that function part is there. So then what we can do is actually integrate it in terms of the y-axis. So we're going to go 1/2 e to the y dy, and we're going to integrate it from log e to the 4 and 0, right? Because we can see that's the y coordinates that would correspond to that. So what we will get from there is that this is 1/2 e to the y. So 1/2 e to the y doesn't really undergo any real changes, which is always good. So we can do that, and we'll get 1/2 e to the y from log e4 to 0, right? So then from there, we'll get that this is going to be equivalent to 1/2 e to the log e4 minus 1/2 e to the 0, which is equivalent to log e4, that cancels out to just 2 minus 1/2, which is going to be 3 on 2, right? So then we have to kind of consider for what's actually going on in terms of our, like, this part of the equation, right? Because we've found this part, we found this section of the equation, but we wanted to find here. So what instead we can do is kind of form a square. So the square is 2 times log E4 as the kind of the dimensions of the square, and we just have to minus the area that we found instead. So we'll end up with just 2 log E4 minus 3 on 2. And that's how it rolls. All right. In terms of the fundamental theorem of calculus, this sometimes comes up in like multiple choice type questions, so it's also a good thing to kind of look after. It's essentially just saying that if we have x to the a, all we have to do is add on that extra bit of x, because this is basically saying the amount of change that it's undergone from here to there. So that's the amount of y that's changed. So that's kind of the section of y that's changed, and this is the original y value. So that kind of tells you what the initial, like the end condition will be. So if we look at something like this, so dy dx equals to root sine where y equals to 1 where x equals to 0, then the value of y when x equals to pi on 3 can be found via evaluating. So what we can actually do here is when we look at this, we'll see that this is the equations that we have, and what we can do is we get the two functions first and we recognize, okay, so that's kind of the initial function that we're looking at, and what we can do is say, all right, so those two are the functions and this is my derivative and this is my initial condition, and then I can kind of name what this is. So then if we wanted to find pi on 3 and try to make that the end result, so what we would put in is y of pi on 3 would be pi on 3 to 0, because that's the next x coordinate we know, plus 1, right? Because that's the y coordinate that we know is coming across. It's kind of like integrating y on the other side. So you're saying the integration of 1 dy from y pi on 3 to 1 is equivalent to the integration of pi on 3 to 0, right, of your root sine x dx. And that's because that's basically what it is. Oh, sorry, root dx. And then from there you can kind of see why the 1 goes across. So then if we try and do that, right, we'll eventually get that when we put this across, we'll see that it's equivalent to this, which is also going to be equivalent to option D here. Alright, another application that has to be considered is when we talk about arc lengths. So arc lengths are essentially when we talk about like the length of the curve, and you just plug into the formula. It's often like if they ask about how far did it have to crawl on the side, you just put into the formula. So it can either be a parametric equation or just a straight one, and either way you can just sub it into the formulas. Okay. Volumes of several revolution, also something that gives people grief. Essentially just work out which axis you're working with and then just find the equation as appropriate and then sub it into the formula. The most important thing with volumes is that you keep it so that it's the same, like you know which equation you're using. So let's kind of talk about the different cases. So if we have volume revolving around the x-axis, so if we have something like this, we'll have something like this, a kind of a cone form like that, say like that, and that's our volume around the x-axis. And for that, we just use our pi y squared, because it's around the x-axis, dx, and this is a, b, and then volumes around the y-axis. A really common one is like making vases, so it might be this kind of thing, making a vase, right? And we just go from wherever, so our b and a are now here, so b, a, and then pi x squared dy. So our x squared means that things are in terms of y, so our x in terms of our y. Right, hollow areas, so that's when we have something like this. So if we have two equations kind of being minused from each other, we have this section kind of being rotated around, what we're actually going to be doing is we're going to be grabbing each of them separately, right? So it will be pi b to a, so this is, once again, this is a, this is b to a, and then we'll have our f of x squared minus our g of x squared. It's not the whole thing squared, right? Because it's not the difference part squared. It's each of them individually squared. So because you're making a donut essentially, rather than you're kind of finding the volume, the outside volume, and then you're finding the inside volume, right? Because that's what the g of x part would be, rather than them being put together and then finding that area that just goes around. You'll find each of the volumes separately and then minus, but because they're over the same terminals, we can kind of combine them together. All right, and this last one, which is hollowed areas and then hollow and a solid area, is if we have something like this. So once again, but we're going over this whole thing, and all we have to do is just split that. So we do the solid area first, right? So that's f of x or whatever, and then we do the hollow area separately. Because before this, we only would have needed really to use f of x, the outside function, versus this one where g of x kind of comes in there, so it can split into two components. Okay, cool. Alright, so that's how our volumes of solid revolution can work. And so, for example, if we considered this being rotated around the x-axis from from x equals to 0 to x equals to 16, we would put in the terminal 16 to 0 and put in the equation. We don't need an extra pi there. And essentially, it would just give us that when we square it, we would get that this is going to just be derivative of x, right? Because it's x squared, root x squared, so we'll get that, and then essentially from there onwards we can get an equation, so it will just be from a half x squared from 16 to 0, so, and that times by pi, so we'll get a pi, and 16 times 16 is 256, yep, so 256, so it'll be 128 minus 0, so just be 128, and don't forget about units cubed. Alright, so if we talked about rotating it around the y-axis instead, what we would have is like rotating around the y-axis, so we'll have this instead. So now we want y equals to 4 and x equals 0, so that's 0 to 4 for this equation, right? So we put in the terminals, 4 to 0, make the y squared instead. So this is just an equation of y equals x squared, so x would equal to plus or minus root y. We can see we're using the positive branch, so it's just going to be our x equals to root y, and then once again it gets squared, kind of very similar to the previous one. We get a half y squared of 4 to 0, so that's going to be pi times 8 minus 0, so it's just going to be 8 pi units cubed. Alright, surface areas of revolution, very, very similar, derived from kind of doing this thing where called like frustrums or something, and then we could basically just cut up the equation into little slices to find the lengths of the curve. So it's kind of like the baby of lengths of curve and volumes of revolution. Okay, so what we can do here is we can pop that equation in for us to use, and we can do the same thing for this one. So we need to find what f dash of y is as well. So we said that x would equal to root y, right? So f dash of y dx dy would have equal to 1/2 of root y. So when we kind of try and sub that into there, we'll get this as 2 pi 4 to 0 root y times x 1 plus 1 over 2 root y squared dy. And then from there, so there's not actually many that you can do by hand for these ones, unfortunately. So get that 2, 4, 0, and you'll get that this is going to be root y times by, this is going to be a 4th y, right? So in order to kind of compensate, you're going to get 4y plus 1 over 4y and dy. So then if we kind of times out that root y, because the root y is at the bottom there, we'll get this is 2 pi 4 to 0, and the root y should cancel out, so we're going to just get that's going to be 4y plus 1 over 4 dy, which now we can kind of use our substitution methods to do, right? Awesome, yeah, and we can kind of progress from there. Alright, so in terms of applications of integration, the main thing is that we just use it for functions that we don't recognize or we know that doesn't have direct integration, and then we just make X the subject, and we can draw and shade and kind of like always just kind of visualize what you're trying to find. These are the equations that you can use. I would recommend having these on your bound notes somewhere just to kind of have a look and be able to see. Okie. So what we covered today, we covered circular functions, differentiation, integration, and then applications of integration as well. Kind of talked about all of those. All right, so please don't be overwhelmed. Thanks so much for listening to this. Practice does make perfect in terms of these. So practice, do a lot of these. Like you saw for some of the questions, when the working out gets really messy and stuff, it can really mess up with how you work out the equation. I'm not sure if everyone feels that or it's just me personally. So really try and structure it and make it clean. Give yourself enough space to write out whatever you need to, and have a look at, like, use a lot of resources, do a lot of exam questions. So just remember to keep persisting, even though it might seem a little bit difficult now. When you kind of get more familiar with it and practice it more, it's definitely something that you can get more familiar with by the end of the year. So thanks so much for listening, and please ask any questions you'd like to.